This video will cover problems 3, 4, and 5 in section 2C. So we continue with more problem solving. In problem 3, we first need to understand what the one son policy is. So just to control the population, and everyone seems to favor having a male child rather than a female child in certain parts of the world, what they have is called the one son policy. So you're allowed to have children until you have one son. So if your firstborn is male, then you stop having children at that point. Now, what if you don't have a male child first? So you have a female child. Okay, so it's a girl. So then you're allowed to try having one more, and until you, of course, have your first male child. So if your second child is a boy, then that's where you stop having children. Now, what if the first two tries, a couple has two girls? So they can continue for the third time, and they can continue having children until they have the first boy child. So if the third child is a boy, that's when they stop. So they can keep having girl children, but the minute they have a boy child, then they stop having children. So this is some method of population control, and let's see how it works by doing a little bit of math. So when we first hear about this policy, if you're not thinking carefully, it almost seems like there will be more girl children on an average than boy children. So that's not how it works. If we do the math, we're going to see that the average number of children in a family is going to be 2, and the number of boys and number of girls is going to be equal. So let's see how this works. Now, suppose we have 10,000 families. So let's assume there are 10,000 families. Now, let's see what happens. What about the first child? We're going to assume that there is a 50-50 chance of having a girl or a boy. So out of the 10,000 families, we're considering the first child. By simple probability theory, half of them will have a boy as the first child, and the other half is going to have a girl as the first child. So let's consider the 5,000 families, which is 50% of 10,000, that have a boy as the first child. So let's look at this table. It gives us some details. So the number of families is 5,000. In these 5,000 families, a boy was the first child. So each family has one boy, 0 girls, because they're going to stop having kids once they have a boy. And the number of children per family then is going to be 1 plus 0, which is equal to 1. And if we consider 5,000 families, each with one child, there's going to be a total of 5,000 boys or 5,000 children in total. The rest of the 5,000 families have a girl as the first child, so they don't stop having kids. They continue to have a second child. So in the first part of our analysis, we notice that 5,000 families have a boy, and according to the one son policy, they stop having children. Now we're interested in the other 5,000 families that had a girl as the first child, because now they're going to continue having children, and now we consider the second child of these 5,000 families. Now again, it's 50-50. 50% of these 5,000 families is going to have another child, which is a boy, and the rest of the 50% will have a girl as the second child. Now, 50% of 5,000 is 2,500. So let's consider these families that had a girl first and then a boy as the second child. This family is going to stop having kids after this point. So let's look at the details of these 2,500 families. The number of families, 2,500. The number of boys in the family is 1. Their first child was a girl, so there's 1 girl and 1 boy. So the first child is a girl, second child is a boy. So total number of children in this per family in these 2,500 families is 2. The total number of children is 2 times 2,500, which is 5,000. So these are the details of um, families that had the second child as a boy, and they're going to now stop having kids. At the next level, we're going to consider those 2,500 families that have a girl as a first child and have a girl as a second child as well. So they are continued or they're allowed to have children until they have a boy. Now we're going to continue our analysis. We're going to look at the third child of those 2,500 families that had a girl as a first child, girl as a second child, and now we're looking at their third child. Now, the third child can be a girl or a boy. There's a 50-50 chance of the third child being a girl or a boy. So 50% of the families will have a boy. That's half of those 2,500 families will have a boy. So 1,250 families will have a boy as their third child, the first 2 being girls. So we are looking at families that have girl as a first child, girl as the second child, and then finally a boy as the third child, after which they stop having kids according to the one son policy. So let's look at the details in this table of these type of families. The total number of families is, and that should have been 1,250. They have 1 boy, that's their third child. The first 2 are girls, so there are 2 girls in the family. The total number of children in the family is 3 times per family is 3, and then the total number of children in 1,250 families is 3 times 1,250. The rest of the 1,250 families who have a girl as the first child, girl as the second child, also have a girl as the third child, so they continue having the fourth child and they stop only when they have a boy child. So now I think you get an idea of how this pattern works. So let's look at the total number of children in these 10,000 families. So we have 1 times 5,000, that was the total number of children from table 1 in the 5,000 families that have the boy as the first child, plus 2 times 2,500. That is the total number of children in the second table. And then we continue with that pattern, and you'll notice that each time we're taking half of the previous number. So half of 5,000 is 2,500, half of 2,500 is 1,250. That we're looking at the second number, and it's multiplied with a number that's increasing by 1. So we have 1 child, 2 children, 3 children. So this is how we calculate the total number of children in these 10,000 families. So when we do the math, we get this number, 19,983.798883. Now, obviously, we're talking about number of children, but I just continue to keep the decimal places until the end when I actually figure out what the average number of children per family is. So the total number of children divided by the total number of families will give us number of children per one family. So total number of children divided by total number of families gives us the average number of children per family. So when we do the math, we come up with this number, and it almost seems like they can continue to have children forever until they get the boy child. But when you really take the average, it comes up to 2. So the population is still under control. So that answers the first part of our question. What is the average number of children per family? And our calculations show that it is just 2. Now, if you think about it, every family has exactly one boy child, exactly one male child. So if the average number of children per family is 2, then the other child would have to be a female. So each family on an average would have one male child and one female child. So even the proportion of males to females is still intact. It's 50-50. It's 1-to-1, which is 50-50. So the one son policy, although it looks a little bizarre, it almost seems like the number of females will end up being more and the number of children per family would increase. When we do the math, it is pretty good. The average number of children per family is is in control, which is about 2, and the number of females is still approximately equal to the number of males, which is how it should be. In question 4, when you read it, the wording seems a little tricky. Brothers and sisters, I have none, but that man's father is my father's son. Who is that man? So let's look at what's given. Look at the statement. That man's father is my father's son. And let's pay special attention to who my father's son is. We're given one more detail. Brothers and sisters, I have none. So I am the only child. Brothers and sisters, I have none. So I am the only child. So the question is, who is my father's son? If I do not have any siblings, then my father's son cannot be anyone else but me. Okay, because I am the only child of my father, because that is given to us. So let's translate this sentence. That man's father is my father's son. And who is my father's son? It is me. So that man's father is me. So if that man's father is me, then who is that man? That man would have to be my son. So here in this problem, you have 12 gold coins. They all look the same. One is a counterfeit, which is heavier than the rest. So there is one coin that is heavy. All the other coins are identical. How can you find the heavy coin when you're allowed exactly 3 weighings and no more on the balance scale? So let's look at how this can be done. We look at step 1. So we are given a balance and we're allowed only 3 weighings. So what we do is we divide the 12 coins into two groups of 6. We place the 6 coins on either side of the scale, it'll be clear to us which is the heavier side. So one of the 6 coins on the heavier side would have to be the counterfeit. We still don't know which one it is. So we go on to the next step. Step 2. We take those 6 coins, again, put 3 on each side of the balance scale. Clearly, we would know which is the heavier side. And since the counterfeit is heavier, the heavier side of the two would have to contain the counterfeit. So now we have 3 coins. We still don't know which coin exactly is the counterfeit. So we repeat the weighing again. Now we have 3 coins. We cannot divide it into two uh, groups of equal number of coins. So we just take any 2 coins out of these 3. Just take any 2. Place the 2 coins on either side. Place the 2 coins on either side, that is, one on each side of the balance. And if the scales tip to one side, then we know that the coin on that side would have to be the counterfeit. That's one possibility. But what if the 2 coins weigh exactly the same? Then we don't need another weighing. The third coin that we still haven't used out of the 3 that contain the counterfeit would have to be the counterfeit coin, the heavier counterfeit coin. So within 3 weighings, we figured out which one is the counterfeit.